yesterday? When we were doing this example, we were just trying to check if these functions were solutions. Can someone just real fast raise a hand in your own words? How do we check to see if a function is a solution to a differential equation? Oh, come on, we gotta wake up. Christian.
You take the derivative of the...
Yeah, take the derivatives of the original. That's good. And then what do we do?
And then we subtract the... or you do like y double prime minus y.
Yeah, and what are we plugging into for that?
Like the original and then the true y for the derivative.
Good. So we take our original functions, we find whatever we need in order to plug into, wait, who's this guy called again? Yeah, the differential equation. So we're just trying to go ahead, and if we're checking to see if something is a solution, and this is also nice because kiddos, remember how we check antiderivatives? How do we check antiderivatives? Yeah. So when you solve for an integral, if you get a function, if you derive it properly, what should it come back to? The inside thing, right? The integrand. And these ones, I'm showing you how to check what we're going to be solving for. Meaning, we're going to be solving differential equations, and how do we check to make sure it works? We can always go through this process of finding whatever derivative we need, and then plugging in, and it should work. This is our way to check our solving of differential equations. Okay, so we did that yesterday. What changed when we had an initial condition? What changed when we had an initial condition?
I found a particular solution.
Yeah.
Right?
We found a particular solution, and how do you know it's particular? Just from looking at it real quick, Ryan.
There's the C that's like, not C, but it's a value.
Exactly. Instead of having a C there, we actually have a number there. There is no plus C, there is no times C. Looking at the original, this one would have been a times C, right? There is no C in the final answer because we solved for it. Particular solution versus general solution. General solution has, like we talked about at the very end of yesterday, general solution has a C still in there. Stands for basically an infinite number of solutions, except they're all related, hence the family. Particular solution, you have some sort of, you have a clue. And when we have a clue, we plug and chug and we solve. True? True. All right, let's keep going. Before we go into slope fields, have your notes packet already. Let me give you actually one more type of example that you guys might see in your section homework, which is due tomorrow, before you actually even get to slope fields. So one more example. That's really off-centered, I apologize. Is that better? A little bit. Okay, the directions are the following. Solve the differential equation, and as soon as you read differential equation, we know somewhere in an equation that we're about to see there has to be differential. What does that point us to?
X's and Y's and Y's derivatives.
Derivatives. There we go. X's and Y's and then some sort of derivatives. Maybe a first order, maybe a second derivative, a second order. Solve the differential equation. Okay, let's just do two of them. Letter A and letter B. Let's do letter A. Y prime is equal to no, that's too hard. That's too hard. What was I thinking? Hold on. Trying to make you guys practice chain rule, sorry. And then the second one, let's go ahead and do ooh, that'll be exciting. Okay. You guys tried the first one. I'll go ahead and help with the second one, because the second one is a whole other version of strange. Not bad, just strange. But before I totally set you guys loose on the first one, what should be maybe your first step to solving? Not checking, but solving. And yeah, this is where we get stuck. Question, who's y prime in differentials? One more time. He's the derivative, and we could say in differentials, he's who over who? Now does this help a little bit? How do you solve?
Multiply the dx over.
Yeah, multiply, go. Multiply the dx over, integrate both sides, right? Don't forget if you're trying to mental math it, you better get it right. You better get it right. Oh, Sarah's on a college trip, huh? I knew that. Sarah's on a college trip, Katrina was at her. Violet and Bridget. Just because we're so dead this morning, ready? I want you guys to check in your groups and make sure you have the exact same answer, but to do so, you have to stand up. Ready, set, go. Stand up and check. Come on, my sleepy heads. I know it's cold outside, but it's warm in here. We should be able to move. I was ready. Ryan, should you? I see. Okay, it's gonna be the basket.
Oh, yeah, I did.
Got it. Lauren, who's you? I like it. Alright, you can sit back down. Come on, my grumpy ones. Hopefully tomorrow you guys can see a picture of my nice scaly foot as I get my cast off. Yes. Hopefully.
Steve, we go get pedicures.
I'll need one at that point. I might need like a descaling treatment. I'm gonna get naked like mold. Anyway. Question. Who was you? I'm gonna go fast. Who is du? Is anybody able to mental math this yet?
Yeah.
To get 1/2 integral of sine of u du? Worst comes to worst, solve for dx, divide both sides by 2, plug it in. And then hopefully you got 2, y is equal to negative 1/2 cosine of, who's u? Plus c. Dun, 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 dun. If you can't mental math it, that's okay. There is no judgment. And if anyone is throwing shade, you shouldn't be. No judgment being thrown. It's better to go slow and steady. Sometimes it wins the race, whereas fast will miss it. Miss the mark. Letter B. Let's do this one together. All right, someone, start me off. What should we probably do first?
Divide dx.
I like it. Now what? It's okay, go for it. What do we do in the other one?
Multiply dx over and throw in that integral.
However, if we throw in the integral right now, why am I going to say like, oh no! What's wrong? What's bad? Who's the mistake? Not the mistake! Who's in the wrong place?
Why?
There are no mistakes. But he's not where he's supposed to be. Being in the problem isn't a mistake. The position is the mistake. How do we move the y over? He doesn't belong with the x and dx. He doesn't belong in that sandwich, right? Let's just do some algebra. Can we just move him and say, hey, you're in the wrong place, buddy? Is that okay? Now, this is new. There's actually a whole section for this. It's called separation of variables. And in our book, it's not until 10.3. But does it make sense that the y doesn't belong? Mm-hmm. Yeah. So move him over with the dy. Okay, now he belongs. Now I throw in the integral. And just to make things easier, let's go ahead and rewrite this a little bit. We have the integral of 1 over y dy dx and the integral of x dx. How do we solve?
1/2 x squared.
Yeah. This one we know, 1/2 x squared plus c equals, on the other side. Now hold on, pause. There are two integrals. There are two integrals, which means I could have like a plus c1 over here. And I could have theoretically like a plus c2 over here. By the way, who would be the integral of 1 over y dy dx? Or sorry, dy? ln of who? Yeah. I could have two different c's, but question, couldn't I do some algebra and couldn't I subtract c2 from c1 and what would I end up getting? C3. Can we just put a plus c on the x side and make that like what we always do if we have integrals on both sides? Is that okay? Let's just leave that plus c over here. Saves us time. Aw, stink. But y's not by itself anymore. That's okay, we know pre-cal. How do we get rid of ln? Wait a minute, e to who? E to everybody? Yes. Because 1/2 x squared plus c is grouped. Here's where I can't just say, oh, pull the plus c out, because it is illegal to randomly pull a number out from an exponent. That would be a horrible math. So we have to go ahead and keep that 1/2 x squared plus c in parentheses, group it all together. Over here on the left, we get just absolute value of y. Over here on the right, we get e to the 1/2 x squared plus c. Let's see how you guys remember algebra 1, even though this is way harder. What does adding of exponents, what does that come from? Or what does that denote? Or what does that signify? Adding of exponents. Multiplying like bases. Oh. So can't I change this to be y equals e to the 1/2 x squared times e to the c? Exponent rules? Wait a minute. E to the c, a number to a number, isn't that just another number? So can't I name him like, what am I at now, like C4? Yeah, I know. But instead of calling him C4, can't I just call him C? So can't I just rewrite this guy and say, oh, that's like C times e to the 1/2 x squared. Oh, that's how a c can be multiplied. Oh, it was a plus c way back here. But the math in solving for y ended up resulting in the c being multiplied. Who's over here on the left-hand side? Absolute value of y. How do you solve absolute value? Well, you say y is equal to positive c e to the 1/2 x squared, or negative c to the times e to the 1/2 x squared. Hold on, a positive or negative c, can't that just be a new c? Oh, so even though we could do all this math, we're going to start making this jump and just basically saying, hey, y is equal to, and c can be, well, it depends on the context of the problem. Sometimes maybe he's a positive, and sometimes maybe he's a negative. Boop. But without more specific information, we'll just say c times e to the 1/2 x squared. Now kiddos, I know, I kind of jumped ahead, but in your homework there are going to be directions that say something like solve the differential equation. Maybe they'll be super nice and give you the dy dx. Maybe. Maybe they'll give you the actual y primey thing. But, one more time, if you see something kind of gross, like this guy, you probably aren't solving him. That's a second order. We're not going to be solving second order differential equations, only first order. If they give you something like that, read the directions. They're probably just saying something like check. Okay, that's all well and good. That's where homework basically begins, but we got to get into our slope fields. Slope fields. This is the technical. It's a pretty technical definition or description for what a slope field is. It's a pretty technical description. This is not going to be a forever card. I know it's in the yellow box. I like how it's stated. I like it better than what I'm about to give you. I'm going to give you the short, sweet, clue-ish version, trick-ish version as to how to think about it. This is a much more technical way of explaining a slope field. To every point x, y in the domain of f, assign a small piece of a tangent line. I'm going to call them baby tangents because it's cuter. And there are fewer words. Assign a small piece of a tangent line, a baby tangent, with a slope defined by So for any given point, you can plug that given point into the derivative, meaning you can plug that point into the differential equation. Then we're going to make, at that point, a small piece of a tangent line with the given slope to some curve that could pass through that point. Can you guys look at your note packet really, really fast? On the very front page of your note packet, what do you see in a graph? Oop, note packet. What do you see on the bottom right-hand corner? A map. What kind of map? Yeah, it looks like wind, right? When would you see something kind of like this? And maybe you saw it this past weekend when everywhere and everyone was talking about the weather. Oh. How can they make some sort of map like this? Do they literally know exactly what the wind is in every single point in space?
Yes.
No. That'd be way too many instruments. But kiddos, what's being shown here now? Weather is partially about predicting what is going to happen. But are there sensors here and there and everywhere that weather people use? No? Does anybody use a weather app? Does anybody use Weather Underground app? For Weather Underground, they actually have different sensors, and I think they have volunteers. I don't think they get paid, but they have volunteers where there are different like measurements where you can see the temperature in different specific places in different areas. It's kind of cool. Think about the same sort of idea. They pick different points and figure out what the weather or what the wind, specifically in this map, what the wind is doing, where the wind is going, the direction of the wind, etc. Now, once again, there is a lot of weather, like meteorology, that's based on predicting, being able to predict where the weather is going to go and the currents, etc. But if you think about it, if they measure what the wind is doing at this point, and at that point, and at this point, and at that point, how on earth can they figure out how it's flowing? Oh, don't they follow the flow of the individual rates? So when we're doing something like, and we're not there quite yet, but when we're doing something like, here. When we're given something like this, it's called a slope field. Don't stress, we're going to get to it in our note packet in just a second. When we're given something like this, and when they're trying to ask us of, or to find, or to match, the slope field with an equation of a general solution. If I say follow the flow, without us writing any more notes quite yet, if I say follow the flow, what do I mean?
Follow paper.
Now, how do you follow the flow? Aren't there tons of flows, kind of, right? You should follow the flow a little better. Not following the flow so well, but aren't there tons of flows? So, first of all, to follow the flow, don't we kind of just have to pick a point if they don't give us one? If they don't give us one, we kind of just pick a point. And then guys, how do we follow the flow at that point? Well, what do you see with the little baby tangent line of that point? Well, hold on. If that's a little baby tangent line, wouldn't that be skimming? And wouldn't these be kind of following? And wouldn't these be kind of following? Now, we're not going to actually like connect and connect and connect, because that's not following the flow so good, right? We're just going to see and kind of try to read in between the lines with our curve. Yeah? Because long story short, are we seeing all of the tangent lines? No, if we were to see all of the tangent lines, wouldn't we get really confused really fast? Right? There's infinitely many. We're not seeing all of the tangent lines, just like a meteorologist can't have instruments or readings at every single location on every single point on the earth, right? That's not going to work. But we can read in between the lines and say, hey, well, okay, I can follow that, and say, all right, here we go. Somehow we're flowing. Question, hold on. What does this flow look like? What kind of function would make this kind of pattern? Yeah, sinusoid. Sinusoid could be a sine or a cosine, right? Stink, let's look at the options real fast. Oh no, they have sine and cosine. Well, stink-a-dink, which one must it be? If we were to start down here at 0, 0, is it starting on the top or is it starting in the middle? Starting in the middle. Who starts in the middle, sine or cosine? Got it. Now, can anybody just looking at, well, if y is sine, can anyone tell me, okay, what differential equation would that, number one, what differential equation would that match to? If y is sine, Oh, so dy dx would be cosine, and the answer would be yes. We're gonna get back to that in just 1 second. First of all, let's write some stuff. That's our little technical definition. So let's go and talk about how we're gonna think about slope fields. And the first thing, before we get to the weird matchy and having all these different slope fields and having to think about who they represent, which y's and which dy dx's, let's first just talk about where they come from. And the best way to talk about where they come from is to make a few by hand. To make a few by hand. And before you guys get super freaked out, even though there are infinitely many points that we could make baby tangents to, we're not going to do infinitely many baby tangents, because that just makes an awful picture to follow the flow with. We're not even going to do tons and tons by hand, because it would take too much time, but we are going to do a few by hand, like a few points, like less than 10, definitely less than 20, probably less than 10 points. Find little baby tangents at each of them and see if we can kind of follow the flow. If it's more than that, they'll give you the table themselves. I apologize. Give you the slope field themselves. So by hand, it's kind of like Algebra 1. Let's go back to a table. It's kind of like Algebra 1. Let's go back to a table. Solving for slopes at particular points. How? Take the point, plug into the slope. So if it helps, the dy dx values, you guys saw it in the page before. We're going to find those by taking the derivative at, this is weird, but it's true. Function notation can represent not just plugging in x's, but also plugging in y's. It's weird, but it's true. So we're going to find our slopes by plugging into the derivative, or another way of thinking about it, by plugging into our differential equation, plugging in each point individually. Mental math is going to come into play. Don't worry, not as much mental math as we're reducing in echelon form matrices. Less mental math than that. Honors is doing that today.
Those are easy, just use your calculator.
Except for the non-calculator part where I make you good. True. You guys know why I made you do that, right?
Sure.
It's a systematic approach. It has you think through the computer programming steps that you would have to tell a computer, put into a computer to have it do it for you simply. You guys are smart enough, not just to use computers, but to actually know how to make them work. That wasn't my whole class, but it was an intro. AP Comp Sci. We should try to get it back.
It was lit. It was rough. It was lit.
Yeah, seriously, right?
All 8 of us.
Juniors, everybody sign up for it, they can be the teacher. Okay, coming back. Sketch baby tangent lines with the approximate slopes. You'll see it when we do it. And then if you're given an initial condition, if you're given a clue, then we can actually, like I did in the one a second ago, we can not just have a general field of slopes, we can actually show the approximate graph of that slope. Sorry, of that particular solution. There are lots of slopes, not just one. So if you're given an initial condition, you can actually follow the flow and get the general gist of what's going on. Now, real quick before we go on, why is this helpful? How is this helpful? We have learned how to find antiderivatives for a select few types of functions. There are literally functions that cannot be integrated by hand. It is not algebraically, mathematically possible. In college calculus classes, they can show you one and actually, in probably Calc 2-ish, Calc 3-ish, be like, hey, guess what, solve this, and like make you agonize over it for forever. And then they'll say at the end, oh, hey, guess what, it's impossible to be integrated. Oh, thanks. There's a huge book that Dr. Teague, if anybody remembers him, Dr. Teague used to carry around because he, as a more of like a physicist, more of an applied math guy, he had this huge book of integration tables. So our forever cards, we have like how many cards of integral formulas? Maybe like 4, maybe 5. He had a book this big, tiny print of integration formulas. That he would say, hey, if I want to solve this integral, okay, let's, like, it's under a certain category, let me try to see if there's a formula for that, and he'd try to go find a formula. Yeah, it's awful. Integration is beast. No, they wouldn't have to memorize that. But there are like lists of integration tables, even in like higher calculus classes, they have you practice taking integrals with all these formulas because they're like, hey, guess what? Integrals are not always this easy. So we do learn how to find some basic ones in AB. We only have to do the basic ones, and the ones we're learning are the basic ones. But long story short, coming back to this, there are some functions that are just in real life. Functions get messy. They're impossible to be integrated. So a slope field lets us know the nature, even the shape of an antiderivative without ever having to actually solve for it. Hence the real life application. Coming back. So let's make a little baby one. One that we could solve. I know. You could solve this differential equation, but I'm not going to give you the really nasty ones because then the slope fields will be really hard for us to do. We're just starting basic. Of a differential equation that we definitely could solve, I have full confidence. Multiply the dx over, integrate both sides. But how do we do it? Step number one, we make a table. Step number one, we make a table. And we put in that table points, and then we find from that table slopes. We plug in points and we get out slopes. Plug in points to who? Well guys, who's dy dx? This guy, right? And whenever you were asked to make a slope field on the AP or in this class, you are going to be given a select number, a select few points to do. Now in this one, how many slopes are you going to have to find? Oh, come on. 12, good. It's a 3x4, right?
Are they going to give us that on the
Yeah.
AP? They're going to be like, here's a 3x3 inches.
No, actually the one most recently that I saw in the AP had, how many points were there? I'm pretty sure it was like 1, 2, 3, 4. I think it was 9. It might have even been just 2.
Okay.
That's the most recent one I saw. They just want to see that you can do it. That's literally all it is. But guys, since they want to see you can do it, you have to be very precise in your approximation. Okay. Someone tell me a point we have to plug in. It's basically up to you guys. 0, 0. All right. We'll start awkwardly in the middle. So that's all right. I probably would do that too. So plugging in the point 0, 0. In this differential equation, we only have to plug in the x, so it's easy. So then plugging in x is 0. 0 squared is what? 0. How do you show a slope of 0 going through the point 0, 0 and keeping it baby? You just make sure it's flat. Right? You just make sure it's flat. Guess what? The APs, if they're checking that, all they want to know is it's flat. That's it. Why is it baby? Because if we do it too long, isn't it going to run into everybody else's? Gotta keep it baby. Can anybody tell who else is going to have a slope of 0? Isn't it any place where the x's are zeros? So wouldn't that work for also 0, 1, 0, 2, 0, negative 1, and 0, negative 2? Oh, we don't even have 0, negative 2, do we? Sorry. Meaning, we're going to have flats everywhere where x is 0. Why? Because the differential equation is only dependent on x. So if we know the x, sweet. All the points on that x equals line, every point for which x is equal to 0, the slopes are 0. What am I going to do for every single point where the slopes are 1? Where do I start? 1, negative 1? One, 0, 1, 1, 1, 2. What are the slopes of all those guys?
1.
Yep. Plug in x is 1. 1 squared is 1. How do I do a little baby tangent with a slope of 1? Well, I think about my point. Let's start up here because it's kind of easiest. I think about my point, right? If I were to go down 1 and over 1, wouldn't the slope be something like this? But I don't want something like that. I want a little baby tangent. So literally my thought process is go down 1, left 1, and in my mind I'm mentally drawing this fact with my pencil, and then I actually connect with my paper and I say, oh sweet. See? Now, I don't draw the dotted line, I'm just showing you what I'm thinking. I'm connecting down one, left one, I'm connecting it with my pencil, and then I start drawing right about here. Does that make sense? So when you guys see me do this, and say, oh, the slope is 1, down 1, left 1, I'm thinking, and then I say, sweet, there he is, right? Go down a point, his slope is 1 too, down 1, left 1, imaginarily, and then start connecting. Down 1, left 1 for the next point. Imaginarily, start connecting, down 1, left 1. These should all be parallel, right guys, if all the slopes are 1? Is that okay? What am I going to do for all my slopes? Sorry. For all my points where x is -1. So I can do -1, -1, -1, -1, 0, -1, 1, -1, 2. Plugging in x is -1, the final answer would just be -1, right? I'm going to go up to this one. Once again, down 1, right 1. I'm going to imaginarily that I'm going to connect. Why? Nice. Way to catch the mental math mistake. We're not just plugging in x, we're squaring it. So -1 squared would be what again? Oh, so these are parallel too? Up 1 over 1? Imaginarily, got it. Got it. Parallel, got it. Got it. Close enough. If I was to ask you an extra question and say something like, oh, hey, let's assume that this, or there is a particular solution given the point 0, 1, sketch the particular solution, what would you do?
Place the point at 0, 1, and then
Follow the flow. Go place a point at 0, 1. Now, approximate has to level out. Does that make sense? If we have a quadratic differential equation that following the flow, the solution would be a cubic. Does that make sense? Oh yeah. Because if the derivative is a square, the original must have been a cubic. Okay, that makes sense. Is that okay? Now this would have been another part to a question. That is not what was originally asked. I was just getting you guys ready. Alright, let's go ahead and in your notes packet, example 2. Now, obviously this thing is huge. Oh my goodness, it's awful. This is worse than an AP would ask. Hey guys, by the way, look at your worksheet. What's the beginning? Oh, lots of little baby draw the slope fields, right? Real quick, on your worksheet, even though it's not due until Monday, the worksheet, you're in your notes, but on the worksheet, can you go ahead and just put down odds? We're not going to do all on the worksheet, it's just going to be odds. So if you guys do want to start on it, say the bookwork is too easy for you, which it might be. Just do odds. But back to our notes, example number 2. Sketch the graph of the solution of the initial value problem. Well, we can't sketch a graph until we have a slope field, right? Stinks. What do we have to do first? Slope field. Now guys, I'm not going to do the entire thing, I'm just kind of modeling it for you, but the slope field, once again, how do we do it? We plug in points to our slope, which in this case would be our y prime equals x plus y. Do you have to show me every single slope? And the answer is no. You do not have to show me every single slope. However, let's just start off somewhere easy, like at the point 0, 0, right here. What's my slope?
0.
0. So what am I going to show you? A flat line. What if I was to go to the point -1, 1? Why am I showing you that point? That's random. -1, 1. Hey, -1 plus 1, what is that? 0. So -1, 1 is going to be 0 also. Can anybody figure out who else is 0 just to save us time in our table?
-2, 2.
-2, 2, that's going to be 0 because add those together. What else is going to be 0? 2, -2. What else is going to be 0? 1, -1? So do you see how you don't have to put every single point in the table? Find a pattern and go with it. Alright, gotta pick somebody else. How about the point 1, 0? Yeah, 1 plus 0 is 1, right? So at the point 1, 0, up 1 over 1, imaginary, then connect. Who else is going to have a slope of 1? 2 minus 1, right? 2 minus 1 is going to work, so the point 2, negative 1, isn't that going to have a slope of 1 also? What else is going to have a slope of 1? 3 minus 2? Hey, I see some diagonal patterns going on, don't you guys? Who else? How about 0, 1? That's 1. Remember, we're imaginarily connecting just in case you forget what we're doing. And then also negative 1, 2. All right. How about the point 2, 0? It's going to go up 2 over 1, imaginary and connect. See how it's a little bit steeper? So imaginary and connect. Who else is going to have that? Do you guys see we can follow our diagonal lines? Approximating a little steeper. We're going to go 3, 0. Uh-oh, that's going to be up 3 over 1. A little bit steeper. It's a little complicated after a while, but long story short, we just have to keep it steeper, steeper as best we can. If we were to go 3, 1, that's going to actually end up being 4, so even a little bit steeper. You'll probably guess this guy's even a little steeper. You guys see my slopes getting steeper along the diagonals? Ah, stink, what haven't we done yet? We haven't gone to the other side. Okay, how about the point negative 1, 0? Negative 1. Oh, that's down 1, right 1. That's this away. You can check it, negative 2, 1, but guess what? That's going to be a negative 1 also. That's going to be a negative 1 also. Once again, still following diagonals. If we go to the point negative 2, 0, that'd be down 2, right 1. Imaginary and connect. So down a little bit steeper. Negative 3, 0, down 1, 2, 3, and over 1, and connect. You can probably imagine we're kind of just getting down, down, down. Now this one's obviously a bit more complicated. What made him more complicated? The fact that the differential equation was based on x and y. But kiddos, did I literally plug every point in? No. I tried to follow patterns. Now, could you plug every point in? Yeah, you could. Can you mental math some of them? You definitely can. But hold on, they actually gave us something else. Do you guys see the other part to it as to why we're not done? What do we do with that clue? We use it. We graph it and then we try to, do you guys see how this means that right here we have to have a slope of 1? Over here it had to even out somehow, because I have this slope of 0 right above. Even out, somehow he's going to be increasing. This is where it gets a little tricky, but then he needs to go downhill somehow. That's close enough. Not perfect, but close enough. But maybe as you guys can notice, depending on where your initial condition is, you might have very different looking graphs. If there is a different initial condition. So not all differential equations, especially when they're based on x's and y's, not all solutions will look as nice and neat and the same. Just something to keep in mind. But if we follow the flow, we're good, we're fine. Okay? That's example number 2. Example number 3. Sketch. We don't need to do that one. Let's go to example number 4. He was kind of fun. We were trying to match stuff. We already matched that. Letter F goes with who? Okay. So number 1 goes with letter F. Y equals sine of x. We did this extra little like, hey, by the way, dy dx would be cosine, but that's not technically our job. Who would number 2 go with? You guys need to remember, pick a point, follow the flow and say, okay, based on my knowledge of basic graphs, who could seem to follow this pattern?
Cubic.
The cubic. Does that make sense? Not logarithmic, not cosine, not 1 over x squared, that would have a vertical asymptote, not a parabola, not a line, not a straight line. Okay. Is that okay? How about example 5 then?
I think that's like, e to the x.
Like
Careful.
1 equals 0.
E to the x.
Yeah.
E to the x?
Ln x.
Ah, you guys are killing me. That's logarithmic. Remember, e to the x goes, swoop, there it is, e to the negative x. Wait a minute, that's a horizontal reflection, which would be moving horizontally. He would look this way, right? Those don't fit that pattern. Let's go find ourselves one of those matching things with dy dx. Nice. Uh-oh, wait. So we're matching with dy dx now, not y?
Oh, shoot.
Now, wait, it's not awful, meaning if you know the derivative is e to the x, what do you know about the original, guys?
See that?
So we could follow the flow on some of them and say, which one looks like e to the x? F. Good. Because I can follow the flow and that looks awful e-ish. Who's someone else that you know the quick antiderivative for?
4.
Yeah, what's the antiderivative of x?
1/2 x squared.
So if you know the antiderivative, maybe you can follow the flow. Who does that go with?
B.
Letter B, because that's going to be a parabola, right? Dilemma. I mean, we can go to number 6 like that also, but what are we going to do with these weird ones that have like y's in them?
Plug in some test points.
Plug in test points and see if they match. What? Like what? Well, hold on. For instance, on number 3, can we take him for just a second? Number 3 is only or solely dependent on who? Do you guys remember when it was dependent on x's? You can go back and look at the example. When it was dependent on x's, did the slopes follow horizontal or vertical lines? Vertical, because x equals are vertical. What's dependent on y going to follow? Horizontal lines like the y equals. Do any of these graphs have the exact same slopes along horizontal lines? Yep, A does, doesn't he? Aren't all the slopes the same as we go horizontally? So what's A going to match?
3.
Number 3. Tomorrow we're going to go ahead and keep on talking about how to do these multiple choice-ish type problems. We're going to keep working on our worksheet. I am going to have you guys write down a few different clues. Here they are. A few different tricks to match. So if you're working on homework and if they say something like, hey, let's match, you can look ahead to the tricks. But remember, homework is less involved in the worksheet. So homework is due tomorrow. Do the best you can with slope fields. It's a little bit of all the examples that we've done. And then we'll keep working on the worksheet type problems tomorrow. Bye guys, see you later.